As we move further into Chapter 3, going through Chapter 3, Section 2, we're going to start putting together and adding on to the concepts that we have already learned. So you're going to see not a lot of brand new stuff, but instead we're going to take the basics that we have started developing and we're just going to expand on them. In 3.1, we focus specifically on graphing quadratic functions. And now in 3.2, we're going to talk about all kinds of polynomial functions. Now, we already learned our parent polynomial functions in the first unit. And we talked about the shapes and that you needed to start memorizing that if you see a V-shaped graph, you know that is an absolute value function. Or if you see, for example, a cubic function, you know that that shape of that graph is going to be that kind of backwards S curve. So that those things are linked in your head and you don't have to try to plot a lot of points to get those basic shapes onto your graph. Remember that we are not using our graphing calculators. I know a lot of high school classes focus primarily on using the graphing calculator, and that's great. But I don't need you to know how to push buttons. I need you to understand how these concepts work together and how the numbers work together so that as you move into higher level math classes, you're prepared to understand the concepts. The further up in math you get, the more conceptual it is and the more importance there is in you understanding those basics. All right, characteristics of polynomial functions. For every polynomial function, the domain will include all real numbers. We saw that with our quadratic function. No matter where the parabola falls, domain is all real numbers. Our graphs are smooth, continuous curves. No breaks, no sharp corners, no gaps. All terms have positive integer exponents. Exponents. That means our exponents, so for example, x to the whatever this is, it's not going to be negative. And it's not going to be a fraction if I have a polynomial function. Those can still be functions, but they are not polynomial functions. The next step, if f of a and f of b have opposite signs, then there is a root, a 0, between them. So basically, if I plug in some value for a and I get out 4, and then I plug in another value for b and I get out -2, well, when I go from 4 to -2, I have to cross the x-axis, agreed? And it doesn't have to be, let's redo that graph. Let's say that I got 4 for this point and -2 for this point. Well, at some place between this x value and this x value, I have to get across the x-axis because I know my graph is a smooth continuous curve. That means that for this to plug in a here and get out a positive and to plug in b here and get out a negative, there has to be a value between a and b that gives me a 0 or an x-intercept. Finally, for all polynomial functions, the greatest possible number of turning points is no more than 1 less than the degree. Now we're going to talk about this later, but just to introduce you, here I have x cubed. This is a cubic function. It is a 3rd degree polynomial. This last point tells me that my cubic function won't turn more than 2 times because I take the degree and I subtract 1 to see how many turns I might have in my graph. Finally, we're going to talk about the intermediate value theorem. This isn't something you're going to have to reproduce, but something that you need to understand because it is what allows us to connect the dots. IVT, the intermediate value theorem, says, suppose that f is a polynomial function and I have a to b that is an interval for which f of a is not f of b. So a to b would be this interval right there. If L is a number between a and b, then there is a number c in that interval so that the value of the function at c is equal to L. This is just what allows me to connect the dots. Okay, let's put some of this on paper so we have an example to make life a little easier. We're going to work with our parent cubic function, f of x equals x cubed. You already know the general shape of this graph. You know that it's an odd function. It's symmetric about the origin because we learned all of that in Unit 1. Let's plug in a few values. Let's do f of 1 would be 1 cubed, which is just 1. F of 2 would be 2 cubed, which is 8. We know f of 0, that's where my vertex sits. If I do f of -1, I get -1 cubed, which is -1. If I do f of -2, I get -2 quantity cubed, which is -8. So I have some plots to point on my graph. Some points to plot. Sorry. So I've got 0, 0, I've got 1, 1, I've got 2 up to 8. So 1, 2, 3, 4, 5, 6, 7, 8, right there. And then when I go the other way, I have -1, -1, -2 down to 2, 4, 6, -8. And that's what my parent cubic function looks like, right? Okay, so now let's talk about this intermediate value theorem. I have this interval from -1 to -2. Let's just pick that. This interval from -1 to -2. And I know that I connect these dots. So, -1 to -2, -1 to -2, this interval right here. And because I know that I connect these 2 points, that means that somewhere between -1 and -2, there's going to be some value that's going to give me a -5. 1, 2, 3, 4, -5 right there. There's going to be some value. The value for this x-coordinate is going to be something between -1 and -2 that gives me -5. I know there's going to be another value that gives me -3. Right? I can plug something in here and get out -3 because I know that I can connect the dots. I don't have to find all those values. There's literally an infinite number of values there. I don't have to find them all. But I know that I can connect those dots because it is a polynomial function. We talked about symmetry in Unit 1. I just brought it up again. But let's review. Our symmetry test is plugging in a -x. If I plug in a -x, I get out 3 options. I get out that, I actually skipped my third option that I'm used to. We're going to add in an option 4. I may have added this in already by the time you get these notes. If nothing happened, not all changes, some change, not all changes, we say we don't have predictable symmetry. We never just say by looking at -x, plugging in -x, that we know we don't have symmetry. Okay, if I plug in -x and I get out the original function, nothing changes, that's even and it's symmetric about the y-axis. An example of this might be the function f of x equals -3x to the 6th minus 7x to the 4th plus 3x 12 minus 12. Notice that all of my exponents are even, so that when I plug in that -x, all those negatives pair up, nothing changes. All those negatives pair up, nothing changes. Those negatives pair up, nothing changes. Constant is constant. By definition, it does not change. So this is an example of an even function. What about an odd function? Well, for an odd function, when I plug in a -x, everything changes so that I get out the opposite of the original function. An odd function is symmetric about the origin. It has origin symmetry. G of x is going to be an example of an odd function. This time, instead of even exponents, all of my exponents are odd, so that they can't just pair up. There's always going to be a negative left over, so that my sign on the term is going to change. So this term would become a positive 3x to the 7th if I plugged in a -x. This would become a positive 7x to the 5th. This would become a negative 3x. So that what happens when every sign changes on every term, I get the opposite of what I started with. Notice that there is not a constant here. By definition, a constant is constant. It doesn't change. For an odd function, everything has to change. So if I see a constant, it cannot be an odd function. We do add one more possibility in Unit 2, quadratic function. Our parent quadratic function is our most basic even function because it's centered on the origin. You can fold it on the y-axis. Once I move that quadratic function away from if I have a horizontal shift so that it's not at 0, now it's still symmetric. But it's symmetric about that axis of symmetry. Whatever my horizontal shift is, that equation for my axis of symmetry, that is where I can now fold my parabola and have both sides match. Again, if none of those things happen, we just say that it's not predictable. All right, let's look at the next page and talk about end behavior. Because the domain of a polynomial function includes all real numbers, it's from negative infinity to positive infinity, most of the function exists to the far right and far left as the function either rises or falls, increases or decreases without bounds. Now, just to think about this, I could have some crazy function here, and it's like, it's doing all this weird stuff, and it's touching and turning, and it's bouncing around, but eventually it's gonna just keep going. And we've got those arrows. Whatever happens in here, all these squiggles in the middle, this is a very limited part of my domain when you think about infinity. Most of my domain happens, most of my function happens out here at the ends, whether the function is increasing forever or whether the function is decreasing forever. This is where most of the function happens. These squiggles in the middle are interesting, but that's not most of the function. Most of the function's out here at the ends, so determining end behavior is extremely important in our functions. We use the leading coefficient test to determine that end behavior, and our leading coefficient test is really simple, really short and sweet. We're going to use this nice little 2x2 chart to determine our end behavior. You're going to examine the leading term of the function when it's not factored. So just glance down here at the bottom. My leading term is going to be the term with the largest exponent. So my leading term, now my math lab sometimes tries to mess with you and doesn't put things in order, so you have to pay attention. If my function isn't factored out, if it's all multiplied together so that you have your individual terms being added and subtracted, your leading term is the term with the largest exponent. Now, those leading terms, we're going to focus on degree, and we're going to focus on the coefficient. So the degree, that exponent, is either going to be odd or even. We're either going to have an odd degree or an even degree. Let's look at the degrees of these examples. We've got a third degree, a fifth degree, a fourth degree, and an eighth degree. 3 and 5 are odd numbers. 4 and 8 are even numbers. So these two functions are odd degree. These two functions are even degree. The other thing we're going to look at is our coefficient and determine whether our coefficient is positive or negative. So if we look back down at these 4 examples, the coefficient here is 5, it's positive. This coefficient is negative. This coefficient is positive, and this final coefficient is negative. So we're looking at degree and coefficient, degree and coefficient, degree and coefficient. Okay, here's what my end behavior looks like according to all of these options. There's only 4 options. If I have an odd degree, my ends go in odd directions. One goes up and one goes down, like that. This end goes up, this end goes down. That is going to be an odd degree polynomial. If I have an even degree polynomial, both ends even out. So they either both go up or they both go down. Now let's focus first on even degree. even degree, the ends even out. They're going to both go up or both go down. Which functions down here are even degree? Well, I see that this one is an even degree. It's degree 4. And this one has an even degree. It's degree 8. So for these two functions, the ends are going to go together. They're either both going to go up or they're both going to go down. Now let's think about this. If it is even and they even out, both go together, and it has a positive coefficient, well, if you're positive, what do? You're happy, and so you smile. So if I have an even degree with a positive coefficient, both ends are going to go up like a big smile. If I have an even degree, however, with a negative coefficient, what happens when you're negative? Well, you frown. So in that case, both ends are going to go down. Let's look at our examples down here. We have 2 that have even degree, so the ends are going to even out. This one has a positive coefficient, so both ends are going to go up. This one has a negative coefficient, so both ends are going to go down. Okay, let's go back and look at our odd degree options. Remember, odd degree goes in odd directions. One goes up, one goes down. Well, which one goes where? If you're positive, you want to have an overall positive rate of change so that, if a line has a positive slope, it looks like that, right? So it starts low, finishes high. If I have an odd degree polynomial with a positive coefficient, it's going to start low and finish high. What if it has a negative coefficient? Well, think about a negative slope, negative overall rate of change. If it's odd, so that it goes in opposite directions and has a negative coefficient, it's going to start high and finish low. So it would be like an overall decreasing function. Okay, down here at the bottom, we have 2 functions with odd degree. This one has an odd degree of 3. And this second one has an odd degree of 5. They're both odd degree, so their ends are going to go in opposite directions. This function f of x has a positive coefficient. So that means that it needs to be overall positive change, increasing function. So it's going to start low, finish high. This one has a negative coefficient, so it overall has a negative or decreasing change, so it's going to start high and finish low. That's my end behavior. If you'll notice, this set of instructions for these 4 examples asks us to do one more thing. It asks us to give the end behavior, the degree, and the maximum number of turning points. Well, if I have a 3rd degree polynomial, I can at most turn 2 times because that's 1 less. If I have a 5th degree polynomial, at most I can have 4 turns in my graph. Now what this means is I don't have to have 4 turns, but I can have up to 4 turns. Where I have a 4th degree polynomial, the maximum number of turns would be 3. Where I have an 8th degree polynomial, the maximum number of turns would be 7. Let's go back and look at that crazy sketch I did at the top of the page, and let's count my number of turns. Okay, I wasn't paying attention when I did this, but we're going to figure it out. I see that one end is up, one end is down, so it's going to be an odd degree. I know that right off the bat. It's going to be an odd degree. I also know it's going to have a negative coefficient because it starts high and finishes low. So I would have a negative coefficient on this function. How many turns do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every time I have a peak or a valley, I have a turn. I counted 10 turns. So my function has to be at least an 11th degree polynomial. It's a smooth continuous curve, so I know it's a polynomial. It turns 10 times, so it has to have at least a degree of 11. Now, it needs to be odd degree, 11 is odd. I would need a negative coefficient on my leading term. So my leading term could be a negative x to the 11th. It might be a negative 13x to the 15th, or a negative 8x to the 27th, but it has to be at least a degree of 11. Could it be degree 12? No, because one end goes up and one end goes down. It can't be an even degree. It has to be an odd degree. The next major thing that we're going to focus on in this section is behavior at the x-intercepts. Now, just be clear, there are two different types of behaviors in polynomial functions that we're focusing on. We can focus on end behavior, that's what we just talked about, or we focus on behavior at the x-intercepts. Those squiggles in the middle, the hills and valleys, those are the x-intercepts. Remember, I've mentioned before, our x-intercepts can also be called roots or zeros of the function. Every x-intercept corresponds to a factor of the polynomial function, and that factor is going to look something like this, x minus a to the k power. Now this k, this exponent on the factor, is what tells me what to expect at that intercept. Now there are only two different types of behaviors. Either it's going to cross or it's going to touch and turn at each intercept. When the graph runs into the x-axis, it has two choices. It can either cross across the x-axis, or it could come in, touch, and turn around and go back the other way. But either way, that's an intercept. If the exponent on the expression, on the factor, is odd, the graph will cross. If the exponent on that factor is even, the graph is going to touch and turn. So in my little sketch here, this shows me what happens if I have an even exponent. It's going to touch and turn. T and T is even, right? So that would be touch and turn. If it's an odd exponent, it's going to cross. Let's do a couple of examples. Now to figure this out, you have to have your polynomial function factored. When it's factored, I don't know what my leading term is. I'm not just given the leading term. I have to figure it out. To get my leading term, when I have a factored polynomial function, I have to think what would happen if I multiplied everything back together. Now, I don't care about doing it. I don't need all the terms. I just need to know what the first term would be. So I'm looking for coefficients. I don't have a coefficient other than 1. And I'm looking for degrees. So this is squared. This would be the first. If I multiply all this together, I would get an x squared. And then I'm still going to have to multiply it times this x. Well, x squared times x gives me x cubed. My leading term is going to be x cubed. There are no coefficients other than 1 on my x's or out in front. That means I have a third degree polynomial. My coefficient is a positive 1. So if it's an odd degree, the ends go in odd directions. It's positive, so I'm going to start low and finish high. That's my end behavior. This is my end behavior. I'm going to start low and finish high because it's an odd degree. They go in opposite directions. It's positive, so it's an overall increasing function. What else do we know based on this leading term? Well, we know that I can have up to 2 turns because the number of turns is 1 less than the degree. Now I'm going to focus on my factors. Well, my factors are x minus 5 and x plus 4. I have 2 unique factors. If I set this first factor equal to 0 and solve for x, I get a positive 5. If I set this second factor equal to 0 and solve for x, I get a -4. Those are going to be the values that are x-intercepts or roots of my function. So if I go over here to 1, 2, 3, -4, or 1, 2, 3, 4, +5, that's where my function is going to intercept the x-axis. What is it going to do at each of those places? Is it going to cross or is it going to touch and turn? Well, 5, this first factor, has multiplicity 2 because that's the exponent. Even multiplicity means I'm going to touch and turn at that place. So over here, when my graph comes into 5, it's going to touch and turn. -4, when I look at that factor, my exponent is 1, so multiplicity is 1, which means at -4, the behavior is going to be to cross. Another piece of information that helps me to graph my function is the y-intercept. I know my x-intercepts. What about the y-intercept? Y-intercept happens when x is 0. If I plug in 0 to that function right there, I have 0 minus 5 squared, quantity squared, times 0 plus 4 just to the first. -5 squared is 25 times 4 is 100. So my y-intercept is 0, 100. You know what, I'm just going to have to kind of make a break and say that I have to skip to get up to 100. This is not, there's a break here. It should be way up. How can I sketch the graph from that? I've given the degree, I've given the end behavior, I've given the maximum number of turns. Now I need to sketch the graph. Well, I know that I'm going to start low and finish high. I know that from the end behavior. I know I have to catch these 3 points. So if I start low, I'm going to cross, come up, make sure I catch that y-intercept, come back down, and when I get to 5, I'll touch and turn, which is going to send me back up for that final end behavior. So I start low, I catch my y-intercept, it's not necessarily the high point, and then I touch and turn and go back up again. So end behavior, start low, finish high. I have 2 turns, maximum number of turns, and I hit my x-intercepts and my y-intercept, and I did the x-intercepts with the correct behaviors. Now, I don't know exactly what this maximum is, this relative maximum here. This is not necessarily it because it's not in the middle. The maximum is probably going to be over here. It's probably going to be more than 100. I don't need that. What I need is that general shape of the graph. Okay, let's look at g of x. Let's look at this next example and see what we can do with it. Okay, so let's look at this next example. First, we're going to decide what our leading term would be if it were all multiplied back together. Remember, we don't have to do the multiplying back together. We just have to think about that leading term. I don't have any coefficients other than 1, so it's just going to be x to the something. I've got x cubed here plus x squared, or no, not plus x squared. I think about adding the exponents. If I were to multiply it all together, the result would be the sum of all the exponents. Don't forget that that is an exponent of 1. So 3 plus 2 plus 1 gives me x to the 6th. If I were to multiply everything together, that would be my leading term, x to the 6th. So it's an even degree, which means the ends even out and go together. It's positive, so they're both going to go up. So my end behavior is going to look like that. Both ends up. It's a 6th degree polynomial function, which means I have a maximum number of 5 turns. So I can turn up to 5 times. Don't have to turn 5 times, but I can. One other thing we haven't mentioned is that the degree tells us how many roots to expect. If I were to write this out as x plus 5 times x plus 5 times x plus 5, I would have 3 roots that were the same, 2 roots that are the same, and 1 root. So in all, I have 6 roots. That matches my degree. 6th degree up to 5 terms. Let's look and see what our factors are. Well, I have 3 unique factors, so I'm going to set each of those equal to 0 to find what those 3 x-intercepts would be. The first one, if I solve that, I get a -5. The second one would be a +3. And this third one would be -1. Those are the locations of my x-intercepts. I've got -5, -1, and +3. Now I need to know what happens at each of those x-intercepts. So I'm going to look at the multiplicity. The multiplicity at -5 is 3 because that's the exponent. It's an odd multiplicity, so the graph is going to cross at that location. It's going to cross the x-axis. My root or 0 at 3 has multiplicity 2. That's the exponent, which is even. So at that value, the graph is going to touch and turn. At -1, my multiplicity is 1. That's an odd number, so at -1, it's going to cross. Now notice that I just made myself notes here, so when I get ready to sketch my graph, I won't mess that up. The other thing I need to think about is my y-intercept. That helps me out. This y-intercept, I can already tell, is going to be really big, so we're going to have to show a break like we done in the last graph. If x were 0, what would y be? Well, if I plug in 0 here, g of 0, I would have 0 plus 5 cubed times 0 minus 3 squared times 0 plus 1, and then just that. Well, 5 cubed is 125, and -3 squared is 9, and then times 1. 9 times 125 is 1,125. So the important thing that we learn here is that our y-intercept is way up there. We're going to have a break to get to that y-intercept again. But that still gives me the shape that I need for my graph. All right, let's think about sketching the graph. We have all the pieces we need. Let's see what the graph is going to look like. Start with your end behavior. I see that both ends are up, so I'm going to start up and I need to finish up. In the middle, I need to make sure I interact with each of these points that I found in the correct way. I need to cross here, touch and turn there. So I'm going to start high. I need to cross, come back and cross again. I need to go way up and catch that y-intercept, and it may even go higher, and then I'm going to come down, touch and turn. That sends me back up so that my end behavior matches what I predicted. How many turns do I have in this graph? Well, I've got 1, 2, 3 turns. That's less than my limit of 5, so we're in good shape. I have 2 relative minimums and a relative maximum with my ends going up forever and ever. Okay. One final concept that I want us to make sure you're aware of. The greater the multiplicity, the more it affects what happens on the graph. Now, odd multiplicity is odd multiplicity, it's going to cross. Even multiplicity is even multiplicity, it is going to touch and turn. But roots with multiplicity greater than or equal to 3 are going to cause the graph to flatten out at that root. So as my multiplicity gets bigger, what happens on the graph changes. Let's think about how this looks. If I have f of x equals x squared, that is an x with multiplicity 2. It's even multiplicity, so it touches and turns. This is our parent quadratic function. So we know it just kind of touches and turns and goes back up. That's what that looks like. Well, what about g of x, where we have x to the 4th? This is still even multiplicity, but now it's multiplicity 4. This is going to look a lot like our quadratic function, except when it comes down to touch and turn, it really flattens out. It doesn't get exactly flat, but it gets really flatter and wider. So the difference is what happens when it comes in to approach the x-axis. Let's think about some examples of odd multiplicity. We have the difference between f of x equals x, x cubed, and x to the 5th. We have multiplicity 1, multiplicity 3, and multiplicity 5. So these are all odd multiplicities. They're all going to cross. But how do they cross? Well, f of x equals x, that's my parent linear function. It's a slope of positive 1 through the origin. It just shoots right across the x-axis. F of x, or g of x, equals x cubed. That's my parent cubic function. It still crosses at the origin, but it doesn't just shoot across like a line. It gives us this curve, like that. So instead of shooting across, we've got this curve where it crosses the x-axis. And finally, h of x equals multiplicity 5, x to the 5th. Well, what's that going to look like? It's going to look a lot like our cubic function, kind of slowed down, where it flattens out when it comes in to cross. You see the difference. It's always crossing if it's an odd multiplicity, but how quickly does it cross? That makes a difference. Okay, final 2 examples down here. We're not going to do the last page together. As always, you have options for what to do with that. For these 2 examples, we're asked to give the degree, end behavior, maximum number of turns, and sketch the graph. So we've got a lot going on here. This first one is not factored, so it gives us our leading term. Our leading term is x to the 4th. Well, x to the 4th, that is an even degree. So we know, and it's positive first term, so we know my end behavior are both ends up. It's a 4th degree polynomial, so we know we have at max 3 turns. To figure out what that graph is going to look like, we have to factor it. So let's think about factoring it out. If I factor it out, I can pull out my common factor of x squared. So I would have f of x equals x squared times x squared minus 4. Well, x squared minus 4 will also factor. It's a difference of squares, so it gives me x plus 2, x minus 2. This original function factors out into 3 unique factors. I've got x equals 0 right here. That's multiplicity 2, even multiplicity. So at that value, we're going to touch and turn. For the next factor, I have x equals negative 2, which is multiplicity 1. Exponent here is 1. That's odd, so it's going to cross. And at x equals positive 2, I also have multiplicity 1, so it's going to cross. The only other thing I really need is my y-intercept, where x is 0. If x were 0, I would have 0 minus 4 times 0, which is just 0. So I know that my graph goes through the origin. That y-intercept is also the x-intercept. Anytime I have a 0 for x, that's my y-intercept as well. Okay, let's look at this. So we have intercepts at 0, negative 2, and positive 2, 0, negative 2, and positive 2. At 0, I touch and turn. At the other 2, I cross. My end behavior is both ends up. So, both ends up, cross, touch and turn, come back. There we go. That's what that graph looks like. Now, I know that I have relative minimums here. I don't know exactly how far down they go. That's fine. On my math lab, when it helps you build the graph, it will fill that in for you. Let's look at g of x, our last example we're going to do together today. This one's already factored. Because it's already factored, we have a head start with the factors, but we need to think about what that leading term would be. If I were to multiply all this together, my leading term is going to be x to the 5th because I add the exponents. That x to the 5th is odd because it's an odd degree. The ends go in opposite directions. It has a positive coefficient, so it's going to be overall increasing. Starts low, finishes high. One end up, one end down. The degree is 5, so I have at most 4 turns. I'm not going to have more than 4 turns. We have 2 unique factors. So if I set each of those equal to 0, I get that x equals 3 and x equals -2. My multiplicity here is 4, which is even. So at that root, the graph is going to touch and turn. My multiplicity here is odd, multiplicity 1, so the graph is going to cross. The last point I need is my y-intercept. G of 0, I would have 0 minus 3 to the 4th power, and then 0 plus 2. Well, -3 to the 4th power is a positive 81, and 81 times 2 is 162. So my y-intercept is 0, 162. Again, I have a break there. I'm intercepting the x-axis at 3 and -2, right there. I know that I'm going to touch and turn at 3. I know I'm going to cross at -2. Where do I start? Well, look to your end behavior. Start low, finish high. Make sure you do everything in the middle that we said. If I start low, I'm going to cross. Multiplicity 4, I need to slow down, come in no, multiplicity 1 here. Over here, I'm going to do multiplicity 4, but I need to slow down, right? Because that slows it down. So I'm going to come in and cross. I'm going to come up and hit that intercept, probably go up further. When I come in to touch and turn, I'm going to slow it down, so it's going to get wide. And then I go up. So that is that little piece where it flattens because of that multiplicity that is greater than 3.